Okay, so let's start our lecture today. So, okay, so, last time we showed that the maximum variation in this rectangle are m or like nm, is exactly given by this mx plus my, right? Where mx is being defined as I think it's maximum x in this rectangle, right? Of the derivative respect to x. Okay. Sorry, it's actually x comma y. Okay. Unfinished. Okay. Okay. So. Okay, I know that. So I also have the expression for this fx and fy, right? Okay, so let me write out this one. 8x a2 squared times negative x squared a2 squared plus 3y squared a1 squared, okay, over 16x squared a2 squared plus y squared a1 squared cubed. Yeah, okay, so this is equal to negative 8 y a1 squared 3x squared a2 squared minus y squared okay, 16 cubed. So, yeah, so I know that these partial derivatives, they so when these xy are really big, yeah, some of them are cancelled out, right? Yeah, so, but yeah, so okay, so how should I analyze this? So let's look at example where you have a function that the derivative is equal to let's say roughly speaking it is 1 over x cubed. Okay. So yeah, so in this case the derivative is well, yeah, so let's say x bigger than 1, okay. So in this case, the derivative is always decreasing, right? So therefore, you may expect. So here we just think about this as just m, mx or m, okay, and then this derivative value is getting smaller and smaller, okay. As sorry, maybe let's say it goes to 0 as x goes to infinity, okay. So okay, example. So then so is there a way to actually control the Riemann sum? So is there any way to control the Riemann sum with the actual integration, right? So namely, is there any way to actually control the like the increment? So okay. To control the variation on each interval of length 1, okay. Yeah, so let me think. So on each so this is f prime x. Wait. So yeah, I was wait. So so here, let's say that this is 1, this is 2, right? So so suppose that this is your, so the function is, okay, so derivative is positive, so the function is increasing, but maybe let's say negative, okay. I think this is a very bad example here because so the function is actually negative, right? So what do I want to think of? Okay, so then maybe just take this fx to be 1 over x cubed, okay? So, and then this f prime x is equal to negative 1 over 3, sorry, negative 3 over x to the 4th power, right? So, okay, so then, let's see, so, yeah. So I know it's look like that, okay. So, okay, so I know that if I integrate from, let's see, okay, 1 to 2, right? So by the fundamental theorem of calculus, f prime x, so dx, okay. So this is going to give me f of 2 minus f of 1, right? Okay. Yeah. So which is the, so roughly speaking, oh, wait. Oh, okay. So it is actually the change of heights. Okay. Yeah, I was thinking of, okay. Okay, so I was so okay. I'm curious about what is so. Yeah, so my goal is to analyze my goal is to basically analyze this area, right? Yeah, so I want to see whether this area is big or small, okay? If it's very small, then I can, yeah, so I can just take the integral of the double integral of xy and then subtract this difference. Okay. Okay, I think the vertical, okay, so the vertical variation, okay. So the vertical variation of each rectangle, okay. Of each rectangle is given by, of each interval, okay, is given by the exactly the this mx, right? Yeah, so this mx, and then because yeah, so you just take the integral of the absolute value of this guy, okay? And then this means what? This means that so the maximum variation is very small, right? It just this guy, right? So so the let's say the shaded area, okay. Shaded area, or like the arrow region, okay. Or like the difference region has so again I'm saying in this case, so has area just less than mx, okay, less than equal to mx. Okay. 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 Oh, okay. Yeah, so same thing would apply here, right? So because here we say that the maximum variation is given by this mx plus my, right? So therefore, yeah. So therefore the maximum difference. Okay. So the error region has volume. Less than equal to I think instead of saying the error volume, the error region, okay, I think it's more I think it's more suitable to say the difference term, yeah. So the difference of the two volumes, right? The different volumes. So there is one volume that's given by taking like either like one of the point inside, right? But like in this case, we pick the like the corner point, right? So in our example, we pick this corner point. So here we're just saying that for any point we pick, right? So it's here. I think it's not just the left corner point because the variation is like it's like the total sense, right? So it's not like it just from any point the maximum variation is always bounded by this guy. Yeah, so the maximum variation is always bounded by this guy. So basically, starting at any point, basically, if you start with the lowest point, right? So I know that the extra. Okay, so if you start with the lowest point, okay. Yeah, so start with the lowest point, which is x mean, y mean, okay. Then so yeah, so this point has the lowest value, right? F of x mean y mean is less than equal to yeah, so what do I mean by lowest value? Okay, so let's say this. Let's just literally say the lowest value. Yeah. For all points in this rectangle. And then okay, so what do you know? Okay, so we know that since the maximum increase is equal to this guy, right? So we know that if I add this term, okay, so this term must be bigger than or equal to f of xy. Okay, so for all xy, yeah. So this is our argument that we made before. So therefore, I have that. Yeah, I think there is an issue about positive or negative. Okay. Okay, let's just do that. Okay. So since so I think there's a sandwich theorem, right? So since we have that yeah, so since this fx min y min less than equal to f of x y less than equal to plus mx plus my. Okay. Plus this. Function yeah, so I'm thinking of if you split the function f plus part, right? So we have, let's say, you have two functions, f1 and then you have f2. So f2 is the function that is strictly smaller, right? Oh, okay. Okay, never mind. So, okay. So yeah, so this is true. Okay. So and then you take the integral over this R and M. So this is equal to 1, right? And then, so this is the actual integral that we care about. Okay. Yes. Okay. So this is equal to, okay. So same thing, okay. Yeah, so this actual integral is actually bounded by these two things, okay. So yeah, so therefore like let's call this x, okay. So this value x is like here, and then this is like f x min. Let's call this a, and then let's call this b, okay. This is a plus mx plus my, okay. So this is x lies between this a and a plus mx plus my, right? And then, so if you pick any, so yeah, so if you pick any other than this point as your Riemann sum point, right? So if you pick any other point, since this is the minimum value, so this point must lies, the function value at this point must lies above this value a here, okay? So this means that the total difference must be, the total difference between this point and the actual function value integral must be bounded by that, okay? Because these 2 points both lies in between, like this line, the a and a plus mx plus my. So yeah, we show that the difference term must be the error region, or sort of error region, the difference, the error, okay. Okay, the error is given this R and M is less than equal to this mx plus my. Okay. Yeah. So the question becomes, how do we, if we can find a way to sort of somehow sum this mx and my, I think we are fine, right? But let me think. Okay, so okay, so how do we actually sum this mx and my up? Yeah, so first we need some way to actually, okay, so So okay, so let's think about a way to actually is this calculable? This term, can we actually calculate this term? I think it goes back to our idea of looking at several regions, right? Okay. Oh. Okay, so we know that, so this is x, okay, so this is y. So, so by our pre-result, so we know that, so, okay, so let's first analyze this, okay, so first let's analyze this fx, okay. Okay, so, and then we use the fact that, okay, so using fact that so this partial f partial x of x comma y is positive when we have the point y is bigger than x over square root of 3 a2 over a1, right? And we have that partial f partial x of xy is negative when y is less than this x over square root of 3 a2 over a1. Okay. Okay, so let's try to locate. Okay, let's locate the minimum point. Yeah, so let's locate this mx in this Rnm. Okay. Okay. So okay, so let's see. So so this is the region 1. Okay, so this is 1 1. Okay, and let's draw this curve. Okay. So this is the curve y equal to x over square root of 3 at over a1. Okay. Okay. So let's say that we are in this region 1, right? Okay. So yeah. Let's rename it. Okay. So let's say this is a region 1. So let 1 be the region of x comma y, where you have x bigger than equal to 1, y bigger than equal to 1, and then okay, and also y is y is bigger than this x over square root of 3 a2 over a1, right? Okay. And similarly, we define 2 to be the region, like same thing, x bigger than equal to 1, y also bigger than equal to 1, and then, but less than, okay. Okay. So this is the region 2. Okay. Okay, so I know that in this region 1, the partial derivative of x is all positive, right? So namely, wait. Oh, wait, no. Okay. Okay. Okay, sorry. I need to analyze what is the maximum of these partial derivatives. So yeah, so what I need is that I just need okay, so can I find the okay. So how can I find these maximum partial derivatives? Maximum one. I know that on the denominator, it seems like So okay, so let's fix one rectangle and see what will happen. So so what should I fix? Okay. So let me fix one pair of points in this one, such that this rectangle is actually fully contained in this region one. Okay. And then, so let's see. So along the line, along the interval, let's see. So where do I want to start? Okay, I want to start with same what they call it, same y value, right? So, but yeah, same y value, but the x value it changes from n to n plus one. Like the x value can move from like between n, like the x value is like the interval, all the interval like n plus one, and the y value is m. So it's like, for example, if you have like these sets like n comma m, and then so you fix like the y value here, and then so this is like n plus 1 m. Okay. So I'm taking this interval here. Okay. Yeah. So let's think about whether this partial x. So now, since I'm increasing along the x direction, right? So what I want is that I want to see, let's say, take the second partial derivative. Okay. So okay, I think it's 256 x squared a2 squared plus y squared a1 squared to the 6th power. And then I take the derivative at the top. Okay. So now I want to expand out. Okay. Maybe. Okay. So how do I write this up? So negative 8 x cubed a2 to the 4th power 24 times xy squared a2 squared a1 squared. So when I'm taking the first partial derivative, I get negative 24 x squared a2 to the fourth power plus 24 y squared a2 squared a1 squared times okay, so times 16 x squared a2 squared plus y squared a1 squared cubed. Okay. And then minus okay, so negative 8 x cubed a2 to the fourth power plus 24 xy squared a2 squared a1 squared times the derivative on the bottom, which is 48 x squared a2 squared plus y squared a1 squared squared times 2x a2 squared. Okay. So let me think. So this cancels out with second power here. So this cancels out. This cancels out. Okay. So what is 24 times 16? So okay, I get 384. Okay. And then times so negative x to the fourth power a2 to the sixth power. Okay. So this is minus, right? X squared y squared a2 to the fourth power a1 squared. Okay. And then, okay, so this term cancels out, right? So this is plus x squared y squared a2 to the fourth power a1 squared. Okay. And then plus y to the fourth power a2 squared a1 to the fourth power. And then, so for this part, so this is okay. This is 96, right? Okay, let's do this. Times. Okay, so here, so this x being multiplied inside. Okay, so negative 8 x to the fourth power a2 to the fourth power. Sorry, a2 to the sixth power. Okay. Okay, and then plus so 24 x squared y squared a2 to the fourth power a1 squared. Okay. Okay, so over 256. Okay. So yeah, so let's distribute the coefficient inside here. So times 8. Okay. So then, so this becomes let's do it together. Okay. So this becomes a minus minus becomes a plus. X to the, wait, what am I writing? So, okay, yeah, okay. Let me write it here. Okay. So let's spread it out. So negative 384 x to the fourth power, a2 to the sixth power, plus 384 y to the fourth power, a2 squared, a1 to the fourth power. Okay. And then plus 768 x to the fourth power, a2 to the sixth power, minus 2304 x squared y squared, a2 to the fourth power, a1 squared. Okay. And then 256. Okay. So yeah, so this just left with 384, right? Okay. Okay. So yeah, I think we can find out something because so this 24, so this is equal to 96 times 4 is equal to this 384, right? So this is, so I can factor like a 6. Okay. So this is like a 6 times that guy. Okay. And what is 96 times 4? Okay. So so here this 96. Where do I get this 96? Okay, I've got. Okay. Yeah. So 96. I think is equal to 8 times 12, right? Times 4 times 3. Okay. Okay. So oh, okay. No. So here, so this is equal to 8 times 16 times 3, right? So I can factor out this 128 times 3, right? Okay. Okay. So yeah. Okay. So so therefore I can okay. So I'm running out of space. Let me think. Okay. So let me just use this one. Okay. So this again. Okay. So I factor out a 384. Okay. Times y to the fourth power a2 square a1 to the fourth power, and then plus x to the fourth power a2 to the sixth power, and then minus 6 x square y square a2 to the fourth power a1 squared, and then 256 to the fourth power. Okay, maybe I should write it out in case I lose track. Okay. Okay. So this one by factoring out a 128, I get 3. Okay. And this one I get 2. Okay. So okay. So let me see what time do I have left. Okay. Okay. Yeah. So I'll just stop here today, and then let's continue next time.